These examples go with Lesson 1, Correlation and Regression. Example 1, fill in the blank, Part A. If large values of one variable are associated with small values of another variable, then the two variables have a what kind of an association? All right, let's take a look at the picture of what's going on. So if we're looking at this on the XY axis, as one variable gets larger, the other one's getting smaller, and so low values of X will have high values of Y. And it'll end up looking something like this right here. And so this is a negative association because as one gets smaller, the other one gets larger. And the reverse of that is true. As one gets larger, the other one's going to get smaller. Part B. If two variables have a positive association, then large values of one variable are associated with what kind of values of the other? Well, again, let's take a look at the picture. There's a positive association going on, so that's going to be something like this heading uphill. And if we look at large values of X back here, then they're going to correspond with large values of Y's right here. So this is going to be large values of one variable will be associated with large values of the other. Example 2. State the type of association that is exhibited in each of the scatter plots: positive linear, negative linear, positive nonlinear, negative nonlinear, and weak linear. Okay, so to be linear means that the dots are going to fall and they're going to suggest a line, a straight line. Now we won't see, dots in a perfect straight line, but they should crowd around something that suggests that a straight line might go through the middle of them. If it's nonlinear, then we're going to be looking for something that maybe curves around this way or around this way. So there's going to be a slight curve to it. Okay? Positive is going to be heading uphill, negative is going to be heading downhill. And then, of course, something that's weak is just going to look like your points are just kind of scattered all over the place and they don't really suggest anything at all. Okay, so for A, I noticed that my lower X values back here seem to correspond with higher Y values up here. This is a negative association. And we can imagine a line coming through right here, and those data points just kind of cluster around it. So A is going to be our negative linear association. Okay, B, the dots are all heading in an uphill direction, so this is going to be positive. And I actually have kind of a little hook going on back here before things start heading sort of kind of in a linear direction. But because of this little hook, we're going to say this is nonlinear. And since it's going uphill, my larger values of X are going to be corresponding with larger values of Y. This is going to be a positive. Part C, I'm looking at my dots right here, and I notice that lower values of X correspond to lower values of Y, and then the higher values of X are going to be corresponding to higher values of Y, so this is going to be positive. And we can kind of imagine a line going through here, and the dots are actually kind of clustering around it. So this one looks like our positive linear association. All right, part D, we've got dots. They're not really, I can try to imagine a line here, but they don't really cluster around that. the line there, and so let's take that out and let's try a different shape. We can try a curve of some sort, and they look like they fit kind of here, but then these down here don't really go with it, so I don't think that a nonlinear is going to be a good idea here either. This one looks like there's going to be a weak relationship or a weak correlation for that line there. So this is our weak linear. And the last one, well, there's only one that we haven't used, and that's our negative nonlinear, but let's take a look at it. The higher values of x are corresponding to the lower values of y, and low values of x are corresponding to high values of y, so that is a negative relationship. And I do actually see there's kind of a curve right through here. So this doesn't really suggest a straight line, but it does look like the dots are kind of hugging around this curve here, and that's what's going to make it nonlinear. So this is going to be our negative nonlinear. Example 3. The National Assessment for Educational Progress, or NAEP, is a U.S. government organization that assesses the performance of students and schools at all levels across the United States. The following table presents the percentage of 8th grade students who are found to be proficient in mathematics and the percentage who are found to be proficient in reading in each of the 10 most populous states. Part A. Construct a scatter plot with reading proficiency on the horizontal axis and math proficiency on the vertical axis. Is there a linear relationship? Okay, the data is actually located here on this slide, and there are our 10 most populous states from California and through North Carolina there. And we're going to draw a scatter plot of this data, and they asked us to put reading on the horizontal axis and math on the vertical axis. That means this is our independent variable, and this one will be our dependent variable right here. So we're going to plot all these ordered pairs. Okay, we want to be careful to scale our graph properly, because if all we do is draw a graph and then say this is 59 and then this is 72 and we have a point here, we could in fact make it look like everything's falling in a straight line when it's not really. Okay, so we want to be sure and have the correct scale. All right, so let's get rid of this. All this stuff in here. Come on. All right, and I'm only going to put in the positive quadrant because we don't have any negative values for scores of reading or mathematics. All right, so we're going to look at quadrant 1. Sorry, I know that's all wavy and stuff. And I'm going to put a little bit of a break in here and in here. This way I don't have to start actually at 0. And I know we had talked earlier about how there are graphs that are misleading because they don't start at 0, but in this case we just want to get a good look at what's going on at the upper end here, and there won't be any graph down here towards 0. All right, so to show that there's a break in a graph, we usually put this little jagged line in here. And of course we have 0 down here, and then I've got a jagged line down here. Okay, and I'm going to scale my x-axis and my y-axis by 2. And I'm going to start at 58. And we got to go all the way out to 80. So 58, 60, 62, 60. Right, that'll take me all the way out to here. And then I'm going to start my vertical axis at 60. And we're going to go all the way up to 80 also. And again, I'm going to scale this by 2. and that's going to put me right up here. All right, so this will be 62, 66, 70, 74, then we'll have 78 right here, and then 80. This is 60, 64, 68, 72, 76, and then 80. Okay, now we can plot all of our ordered pairs. Okay, let's back up here. The first ordered pair I have is 60 and 59. All right, so 60 is right here, and 59 is going to be slightly below my 60 right here. And then my next point I'm going to plot is at 73 and 78. All right, so I'm going to come out here. This is 72, so 73 is going to be right in here. And 78 is right in here, right by the 78 line right there. Okay, and now I'm going to put all the rest of the dots on here. Okay, so now we have all the points on here, and you'll notice if you count them, you can only see 9, and that's because we had one of our points, and this was the one that was at 75 and 70, so that is this one right here. We actually had 2 of those, so there are 2 data points that occur right here at this point. Now, our question was, do we have a linear relationship? And if we take a look at this picture, do my points suggest a straight line? In other words, can I imagine a straight line coming through here and my points are kind of clustering around that line? And the answer is yes. We do actually have a straight line in here, and these points are fairly close to it. So we can say for part A, the answer is yes. There is in fact a linear relationship between the two. Okay, now B is asking us to compute the correlation between reading proficiency and math proficiency. And then we're supposed to determine if the linear association is positive or negative, and if it's weak or if it's strong. Okay, so what I'm going to do is I'm going to pull up Excel, and I'm going to let Excel do the work for me, because I'm going to show you how to do this using the formula, and then I'm going to show you how your calculator can do it for you. Okay, so over here in Excel, I've already put the data in, as you can see, and our formula is we're supposed to find the mean for our x values, we need the mean for our y values, we need the standard deviation for our x values, and we need the standard deviation for the y values. And so I'm going to do that first of all. Actually, before I even do that, I am going to do a count command here that is going to tell me how many data points we have. Now, we already know that there's 10, but the reason I put this in here was because if this number was going to be something else, if we wanted to add some more states in here, then this number would automatically increase on its own. I don't have to go back and do it by hand. And I'm going to do one over here as well. I'm going to put a count command in here. B2 to B11. All right, so we know that there are 10 items in each of my lists there, X and Y. Okay, now the next thing I'm going to do is I'm going to figure out what the average or the mean is for my X values. Okay, remember Excel has that command equals average, and that's what I'm going to do to figure out what the mean is for my X value. So we're going to do equals average, and all of my data occurs between A2 and A11, and it gives me the mean to be 71.8. We also need to know the standard deviation for our X values, and remember Excel has a command for standard deviation. This way I don't have to do the diagnostics in the data analysis, and I can call up these cells when I want to do stuff with them. Okay, so the command was equals STDEV, and you'll notice we have 2 of those there we've got stdev.p and .s. We want the .s because this is from a sample. Okay, all right. And again, my data goes from A2 to A11. And it gives me my standard deviation, and I can tell it to round anywhere, but I'm going to go ahead and leave it at those 6 decimal places right there. Okay, let's go in here and do the same thing for y. Remember, we're going to do the average or the mean first, so equals average. Now, all my y values take place between B2, and you'll notice it's colored blue now, and they go all the way to B11. And you'll notice that now the entire y column has been colored in. So that tells me where I'm finding the average. And it's giving me the average for the y's to be 70.1. And I need a standard deviation for my y's. So I'm going to do the Excel command equals stdev. Again, we're doing .s because this is a sample. And then again, all my data goes from B2 out to B11. All right, and there's the standard deviation for the y's. Okay. Now, what we're going to have to do is we're going to have to take each x, subtract the mean, divide it by the standard deviation, and then we're going to have to take each y, divide it by the mean, and times it by subtract the mean, and then divide it by the standard deviation, and then we're going to have to multiply all those together. And then we're going to have to add all of those together, okay? Because the formula, which is back here, very intimidating looking. All right. Here's our formula to find the correlation coefficient. We have found this right here. We found this right here. We found this right here. And we found this right here. So now what I have to do is I have to go through and calculate each data point minus the mean divided by the standard deviation. So I'm going to have to do this 10 times. And then I'm going to have to do the same thing in the y column. I'm going to have to take each y value, subtract the mean, and divide it by the standard deviation. And I'm going to have to do this 10 times. And once I have that done, then I have to multiply them together because these two sets of parentheses have to be multiplied. So I'm going to have to take each of these 10 and multiply it by each of these 10. That's going to give me another column. And then I have to, this thing right here means we need to add stuff. So then I'm going to have to add all those products together. And finally, back here, we're going to multiply by 1 over n minus 1, or we're going to divide by n minus 1, however you want to take a look at that. All right, so let's go back to Excel and to our spreadsheet and see what we're going to do. All right, in column C, I am going to subtract each data point in the X column minus the mean there. So I'm going to take A2 and I am going to subtract A13. Now, I'm going to put dollar signs on here, and I'll tell you why in just a second. And we're supposed to divide this by the standard deviation, which is down in A14. And I'm also going to put dollar signs on this one. All right, and that's what it's going to give me. This negative 1.96788. Okay, now when we come up here, you'll notice that there's a little box right here on the corner. If I grab a hold of that and press down my left click and drag this down so that it covers all of my data, it automatically populates each of those cells for me so that I don't have to go through and type that formula every time. Now, notice up here in the box where I've typed in my formula, I have $A13, $A14. Well, why did I do that? Because in the next one, when I copied it, I still have A13 and A14. And when I go to the next one, I still have A13 and A14. So the only thing that's changing is this first one here. We got A4, now it's at A5, but we still have A13 and A14. So what the dollar signs do is they tell me to use this particular cell every time and to use this particular cell every time. And since my first one doesn't have any dollar signs on it, whenever I copy, it automatically moves on to the next one. So if we're on A2, then it moves to A3. If we're on A5, then it moves to A6. Okay. Now, in the next column, I'm going to do the same thing, but I'm going to do it for my y's. So I need to take each of my y values, and in this case, we're looking at cell B2, and I am going to subtract. Now, I want to subtract the mean for the y's, and that's located in B13. But I'm going to be subtracting that every time. So we're going to do the dollar signs in here for B13. And then I'm supposed to divide this by the standard deviation for the y's, which is located in B14. And again, I'm going to use dollar signs. And you see everything over here that's highlighted. That's what I'm using to calculate this particular cell. And this is what it gives me, negative 1.81964. All right, once again, I'm going to highlight this box, and I'm going to grab that little square, hold down the left click, and drag this straight down so that it covers all of my data. And then it populates all of my cells. And I can come in here and check my formulas and see I still have cells 13 and 14, but I've moved on to B3. And I still have cells 13 and 14, but I've moved on to B4. And I still have cells 13 and 14, but I moved on to B8. So I'm pretty satisfied that I have exactly what I need right here. Okay, so let's go back to the formula. And let's see what we've done. Okay. All right, let's get all this out of here. Okay, so over in the Excel spreadsheet, I have now performed this calculation for all of the x values, and I have performed this calculation for all of the y values. So the next thing I need to do is to multiply these two things together. All right, let's bring up our Excel spreadsheet. Okay. All right, so this is my x calculations. This column has my y calculations. Remember, I need to multiply those together in my next cell here. So I am going to take cell A2, and I'm going to multiply it by cell B2. And you see it's highlighted the two cells that I'm using. And there is my product. And I multiplied the wrong ones. I was supposed to multiply C2 and D2. Sorry. Let's try that again. All right. We're going to take cell C2 and multiply it by cell D2. There we go. And there it gives me my product. And I'm going to highlight this and grab that little square and drag it on down here, like so. All right, now I have all of the products here. Okay, the next thing that my formula told me to do, once I have all my products, I need to add them together. That's what that little sigma sign says. Okay, so down here, I am going to add together all of these numbers in column E. All right, so this is, we're going to add together E2 to E11. And there's what I get. And then finally, to get to my R, and this is what it had asked me to calculate, we need to take cell E12. All right, so we're going to take E12, and we are supposed to divide that by n minus 1. Well, remember, we've already figured out our n. We did the count back over there in line 12 for A and for B. That was 10. So we're going to be dividing by, and I'm just going to put A2. Oops, I better put this in parentheses. A2 minus 1. Okay, let me try that again, because I'm supposed to be using this cell here, A12, not this cell up here, A2. So let's try that again. We're supposed to be using A12. There we go. Okay, and here it is. This is what they were asking me to calculate, the correlation coefficient, and it is 0.808623. Now, normally we just round this out to 3 decimal places, so we could call this 0.809. Okay. All right, so now the answer to part B. We said the correlation coefficient R is equal to 0.809. Is the linear association positive or negative? Well, we could have told that by looking at the scatter plot. Since the points are heading uphill, in other words, my higher x's do correspond to higher y's, then we do actually have a positive correlation here. But because the R value is positive, we can also say that the correlation is positive. Okay, and then is this a weak or a strong relationship? Well, normally we say that a strong correlation is more than 0.075 or less than negative 0.075. And since 0.809 is greater than 0.75, this is a pretty strong relationship. Example 4. For which of the following scatter plots is the correlation coefficient an appropriate summary? Okay, in part A, we have our dots right in here. Our larger values of x seem to correspond to larger values of y, and our smaller values of x seem to correspond to smaller values of y. So it looks like we have a positive relationship here. We can imagine a line going through here like so, and all of these points seem to really cluster around that line. So A is appropriate to have a correlation coefficient. All right, let's take a look at B. For B, we have a negative relationship from here down to about this point, and then we suddenly have a positive relationship. Okay, and we have a curve here. So because of this curve, we're going to say our correlation coefficient is not going to be appropriate because our correlation coefficient corresponds to linear relationships. And this one, as you can see, is not going to be a line. All right, for C, we have our dots right here kind of clustered around, and then we have this guy out here that's, I don't know, doing his own thing. Now, we can imagine a line coming through right here, and all of these points kind of cluster around it. But like I said, we got this one right here, which is considered to be an outlier because it is the only one that's doing this while all the rest of them cluster around. And if an outlier is present, we do not want to use the correlation coefficient because this guy right here can actually throw off our correlation coefficient and make it so that it does not really represent our data. It would actually take this line and it would move it probably in this direction some. Example 5. An economist discovers that over the past several years, both the salaries of U.S. college professors and the amount of beer consumed in the United States has gone up. Thus, there is a positive correlation between the average salary of college professors and the amount of beer consumed. The economist concludes that the increase in beer consumption must be caused by professors spending their additional money on beer. Explain why this conclusion is not necessarily true. Okay, so we can see the obvious absurdity in here. I mean, just because they have a raise doesn't necessarily mean they're going to be spending their money on beer. But the fact that their salary has gone up and beer consumption has gone up means that there is a correlation between the two, if we were to try and graph them on the same scatter plot. However, that doesn't mean that one is causing the other one to happen. Okay, correlation and causation are not the same thing. Correlation means we can see a relationship between the two and it's either positive or negative, but it doesn't really tell me if one is causing the other one to happen or not. Okay, so the main reason why we would say this conclusion is not necessarily true is the fact that, well, college professors are not the only ones that drink beer. That's one of the reasons. So our college professors are not the only beer drinkers here. In fact, part of this could be due to the fact that enrollment is increasing in universities, and maybe the students are drinking more beer because we have a larger enrollment in the universities. Larger enrollment could certainly lead to salaries increasing, because if there's larger enrollment, then the professors will be teaching more classes or teaching more hours, and so we can say that they have the positive correlation because of that, but the fact that there are other people who drink beer other than the professors, we can't say that one causes the other one to happen.